Hi, we're here to tell you about MEERs for Earth's energy rebalancing, better known as the MEER ReflEction project. It's a solar spectral eco-engineering project that could save humanity. We are members of the EFP Education, Finance, and Policy team. I'm Isabel Wellington, a senior at UC San Diego. I study environmental systems with a specialization in environmental policy.
Hi, I'm Sophia Morgan. I am a senior at the University of California, San Diego, studying cognitive and behavioral neuroscience.
Hello, my name is Skye, and I'm currently attending the Bronx High School of Science. In the future, I plan on pursuing a degree in STEM.
Here we have the outline for the presentation. We're going to begin with the motivation for the project, which is climate change. Then we're going to go into what the project is, how we need to develop it, and the timeline.
Climate change is defined simply by NASA as a change in global temperatures and weather patterns due to natural fluctuations and human interaction.
There are two existing human responses to climate change. Mitigation, we have two definitions for. The first being reducing and stabilizing the levels of heat-trapping greenhouse gases in the atmosphere, and the second being stabilizing Earth's temperature to the most optimal habitable conditions. The second human response is adaptation, defined as preventing or minimizing the anticipated or ongoing effects of climate change. We like to consider the MEER ReflEction project the combination of both of those, which we call adaptive mitigation. We define that as stabilizing Earth's surface temperature while preventing or minimizing the anticipated or ongoing effects of climate change. So let's go a little bit more into mitigation. Examples of this would be restoration, so restoring damaged ecosystems, establishing new ecosystems, greenhouse gas reductions. Mitigation is often seen in action plans, which is a formal declaration of how the mitigation actions will be deployed, prioritized, and administered. There are environmental impact reports, which projects are required to give to the government when they are affecting the environment. In these, they list existing or proposed operations, alternatives to the outlined operations, and proposed methods of mitigation. The steps to develop an action plan are identify the goal, identify potential actions, and then develop the plan itself. Adaptation. So examples for this would be assisted migration and dispersal of species, GMO crops, so crops modified to handle increased CO2 levels, increases in temperature, drought. Geoengineering, or the large-scale manipulation of Earth's climate system, is often considered a subset of adaptation, and that creates a large range in project size for adaptation because most are on a small sectorial scale, while geoengineering is on the global scale. I'm going to hand it over to Skye so he can discuss the current popular methods of geoengineering.
This is a diagram that I made to classify how geoengineering techniques fit with regards to energy flow. As the image shows, solar radiation is the major source of energy that powers our climate system. This incoming light is also known as shortwave radiation. Some of the sunlight is naturally reflected by the atmosphere and the Earth, but the majority is actually absorbed by the surface, causing a warming effect. Additionally, the Earth's surface could also emit infrared radiation back to space, which is depicted in the image as the red waves. This outgoing energy is called long-wave radiation. The greenhouse effect on Earth is essentially caused by infrared radiation being trapped inside the Earth's lower atmosphere. When this happens, the energy does not leave our climate system and is re-emitted back to the surface. Instead, by allowing long-wave radiation to escape, the harmful greenhouse effect is stopped. In this section, we decide to highlight each of the major solar radiation management technologies to assess the category that Project MEER ReflEction falls under. Going by height, the first solar geoengineering technique are space-based methods. As of now, the main proposal for space-based methods are space mirrors. What space mirrors does is essentially reflecting incoming sunlight miles and miles in the atmosphere. However, mostly due to cost concerns, space-based methods are highly unlikely to be implemented. Another type of solar geoengineering, and arguably the most popular right now, is stratospheric aerosol injection. This technique aims to spray sulfates into the stratosphere, which then can be used to reflect and disperse incoming sunlight. The inspiration behind this idea is a natural phenomenon of volcanic eruptions. When volcanoes erupt, they emit tons and tons of particles into the atmosphere, which has been known to bring down temperatures on Earth. Most of the stratospheric aerosol injection technologies vary the method used to bring a material into the air and the type of material released. The next type of geoengineering is marine cloud brightening. Like the name says, the purpose of marine cloud brightening is to make marine stratus cumulus clouds brighter. By doing so, the clouds would have a greater reflectiveness in regards to incoming sunlight. Currently, the leading way to do this is to spray salt water into the air, which can then act as nuclei for new clouds to form. After this is surface albedo modification, which can be broken up to crop albedo modification, desert albedo modification, and urban albedo modification. What all these techniques have in common since they all aim to increase the reflectiveness of Earth's land surface. Moving on, the next solar radiation management technique are microbubbles. This proposal plans to inject extremely small bubbles to the surface of the water, increasing the thickness of seafoam and making the ocean more reflective. This initiative is based on natural bubbles already in the ocean, also known as undershine, which reflect a small amount of incoming sunlight. Other than increasing the reflectiveness of the Earth's surface, microbubbles can also conserve bodies of water by reducing its evaporation. The final type of solar geoengineering in this section is cirrus cloud thinning. This is the only major solar radiation management proposal to interact with long-wave radiation rather than short-wave. What cirrus cloud thinning does is decreasing either the opacity, frequency, or duration of cirrus clouds, which absorb more outgoing sunlight than reflecting incoming sunlight. As a result of this property, scientists have proposed adding ice crystals into the air to decrease the amount of water vapor available for cirrus clouds to form. Again, this would allow for more infrared radiation to travel out to space. These tables show a summary of how feasible each of the solar radiation techniques I mentioned before actually are. In green are the physical characteristics that, when checked, is a positive aspect. In red are the environmental consequences that, when checked, are a negative aspect. I do want to highlight termination shock. If a large cooling effect were to occur due to implementation of geoengineering and then suddenly stop, a rapid period of warming would follow. The rate of warming would be much greater than it would be without deployment at all, and less time for society to adapt to change.
There are three areas of rejection: philosophical, technical, and ethical. Philosophical would be thinking that it's playing God, the potential weaponization, the current lack of government. Technical is mostly a lack of literature in many different areas, which I'll get into in a minute. Ethical would be the social implications, the unknown risks, or the fact that sometimes it's considered a mitigation deterrent. Geoengineering has been a topic of discussion a lot in recent years, mostly because people worry about the development of it, but also see that it may be necessary because mitigation may not be enough to reverse the damage that's been done to Earth. Here you can see that effectiveness, politics, the termination effect, which Skye just discussed, and the need for transparency are all things that seem to be themes among the discussion of geoengineering. The lack of literature probably being the biggest one. There are four categories that I decided to divide this into. The first being governance. So the lack of governance currently happening, the fact that a lot of geoengineering projects are different and therefore would require more individualized governance. The second is regional climate response. So that would be spatial distribution and how that affects different areas of the world. The third is biodiversity impact, so how the projects affect the biodiversity in the areas that they're in, the areas that they're not in, and so on. The fourth is cost. So projects often fail to provide long-term cost projections past the research and development phase. Despite the concerns that surround geoengineering, there has been a lot of development in the recent years. The United States is a great example of this. In 2009 to 2010, they had their first congressional discussion. In 2017, the first proposed geoengineering legislation passed into law, and just this year in 2020, the first government-funded geoengineering project was created. So let's get into the MEER ReflEction project. What is it and why is it viable?
MEER ReflEction is a grand, versatile, and comprehensive engineering project feasibly rooted in the ecological functioning and resource availabilities of planet Earth. Our project addresses the imminent pressures of climate change while shifting energy production and consumption to renewable energy. At its core, this project is essentially implementing strategically placed mirror arrays on the Earth's surface to reflect sun rays back into space. For any mirror, when photons strike its surface, the photons are then reflected back at the same angle. This seemingly simple underlying principle is the main notion on why our idea is plausible. What makes mirror reflection different from other solar geoengineering techniques? In order to address this question, we've constructed a diagram to show our project's unique benefits. Starting from the top, our mirror arrays will be durable and thus termination shock-free. Unlike many of the other methods proposed, our project is stable and stays in place. A second benefit is that we allow for sustainable agriculture. Other solar geoengineering initiatives take place in Earth's atmosphere, potentially blocking incoming sunlight from reaching fields of crops. Project MEER ReflEction also places a strong emphasis on ecological restoration. Through the implementation of our project, we are able to restore conditions of ecosystems back to sustainable levels where biodiversity can thrive. Next, our project would inhibit positive warming feedback that occurs in places such as the Arctic regions. In other words, layers of ice would melt at a significantly lower rate. A final aspect that is unique to our project is that we are 100% renewable. This is because we can effectively reflect sunlight in each array to a central location, where this energy can then be harnessed as power. With that, I'll pass it back to Isabel, who will talk about how we will address geoengineering concerns.
Well, for regional climate response, we are researching the impacts of our spatial distribution. For biodiversity, we are addressing the impacts our project will have on the biodiversity around our MEERs. For cost, we are developing long-term cost projections. So for governance, geoengineering has been addressed a lot more recently in terms of policy. But outside of that, we have a policy team which will be addressing policy concerns, how this could be implemented in terms of policy, and whatnot. So what do we need to get started?
My focus on the project has been how we will support Project MEER financially. So we have broken this into 3 big questions. How will we obtain funding? Where will our funding come from? How much funding is needed? And what will it be used for? We have been looking into 4 categories of funding, which each have pros and cons and will ideally be used for different aspects of our project. Government funding has many opportunities. However, grants provided are often smaller scale than what we would need to encompass our project as a whole, and they have long cycles, which would require applications once a year. Research grants will be useful. They are also often pretty small and have really specific categories, but we would like to use these going forward to support projects done by each of our teams. Independent foundations often provide large sums of money for projects such as ours, especially those relating to climate change, and would be beneficial for our research and development stages, particularly. Business partnerships will allow us to work with companies during implementation stages. However, they will expect an immediate return on investment, which won't be guaranteed until later in our project future. So how much do we need? We have calculated we need roughly $20 million per year of research and development, totaling $60 million over the next 3 years. How is this broken down? Our first year brings non-recurring startup costs. Our 4 main categories of costs include 28% for office and lab space, 25% for startup equipment, 22% for personnel, and 18% for equipment and supplies. Our second and third years will include costs for office and lab space, personnel, equipment and supplies, and professional services. So personnel will be a significant part of our cost for all of our years. Our first year, the project will consist of 10 teams of roughly 7 people, made up of 2 PhDs, 2 grad students, and 3 interns. Our second year, we will bump up to 10 teams of 10 people, consisting of 3 PhDs, 3 grad students, and 4 interns. Each team will need $100,000 in disposable supplies per year and $200,000 in equipment per year. We are also accounting for 1,000 square feet of office space per team and 150 square feet per person of office space. Overall, there will be $5 million in renovation costs and $2.3 million in rental costs per year. We also have startup costs, including equipment and software licensing, which will account for $5 million of the first year's budget. There are also some smaller costs associated with the project. First, $100,000 will be allocated per team for professional services, with an additional $50,000 for legal fees and patents per team. Next, each member will be expected to travel at least once a year for conferences and other talks. Each of our 10 teams will have researchers and 1 leadership member. Each researcher will travel once a year, and each leadership member will travel twice a year. The educational outreach and public relations team will travel twice as much annually. We've calculated that domestic travel should cost about $1,200 per trip, and international travel will cost $3,000 per trip, for an average of $2,000 per trip.
One of our goals in Project MEER Reflection is to inform as many people on our initiative as possible. This conference, for instance, is one way we are doing that. In order to have the biggest target, we had to ask ourselves, how do we plan on building a media presence? How will media help the project? And how will we educate the public on our initiative? The main way we are getting the word out on our project right now is through our website, which provides a central gateway for the public to learn more about it. You can even view it right now at www.meerreflection.com. It includes general information about what we are doing, project updates, and even a section where you can contact the team for further information. We also plan on launching YouTube and social media accounts in the future. Geoengineering as a whole has not made that much of an impression on any of these platforms, and we plan on changing this. There is an entirely new generation of young scientists, such as myself, who we believe need to learn more about these technologies. Finally, one of the best ways to increase our media presence is through the press. In the future, when Project MEER Reflection gets closer to implementation, we plan on having reports on our initiative on as many news sites as possible.
So, how long will this take to deploy? So, for the rest of 2020, our goals are to communicate our findings to our academic circle as well as to the public in order to get the name of Project MEER out there and to inform people on what our plans are going forward. And then 2021 through 2024 will be our research and development stages to prepare our technology and assess feasibility of the project. Full-scale implementation will be started by 2025, and by 2030 we will have full implementation.
Thank you for watching our presentation, and if you have any more questions or want to see more about the project, feel free to go to meerreflection.com.